this problem is a little more involved than the other two. We have two streets that intersect at right angles. And a police car is traveling from the north towards the intersection. Okay, and that is a right angle. And we have a speeding car that is moving straight east away from the intersection. Okay, when the police cruiser is 6/10 of a mile north of the intersection. All right, so we're going to be talking about the distance from the police car to the intersection, which should be decreasing. Okay, and that first part of that sentence says when y is 6/10 of a mile. Let's see, the speeding car is 8/10 of a mile to the east, so the distance from the speeding car back to the intersection is also changing. So that's going to be x. They're telling me when y is 6/10, x is 8/10 of a mile. And the police determine with radar that the distance between the police car and the speeding car is increasing at 20 miles per hour. Now, I haven't drawn that distance yet, and that would be represented by that segment. That distance is also changing, so I'm going to give it a variable, z. So the distance between them and the car is increasing at 20 miles per hour. That's giving me some information about the rate of change of z. That's 20 miles per hour. If the police cruiser is moving at 60 miles per hour, that's telling me about the rate of change of the distance y. That rate of change, the speed is 60, but the rate of change would be negative 60 because the police car is getting closer to the intersection, so that distance y is decreasing. And then our job is to figure out the speed of the car, dx over dt. So again, start with an equation, x squared plus y squared equals z squared is going to give us the relationship between all the quantities in this problem. Take a derivative with respect to t. And since everything is multiplied by 2, I can divide by 2 to simplify the equation I've got to deal with. All right, we know a value for x. We're looking for dx over dt. We know the value for y and dy over dt. We don't have a value for z, so we're going to have to figure that out. And we know the value of dz over dt. So now thinking about what is that distance z, when x is 8/10 squared and y is 6/10 squared, that has to equal z squared. So if you solve that equation for z, you'll find that z is equal to 1, which is convenient. All right, so we're looking at the equation. 0.8 times dx over dt minus 36 equals 20. So 0.8 dx over dt is 56, and dx over dt is 56 divided by 8/10, which is 70. So the car is traveling at 70 miles per hour. One last example. Again, pause the video to read the problem if you need to. In this problem, we have a cone-shaped water tank that water is pouring into. So I'm going to draw a cone, and this water tank stands point down. So the base or circular part of the cone is the top. And so our water tank looks like that. Okay, if the water is running into the tank at 9 cubic feet per minute, that's telling me about the volume of the water in the tank and how that's changing. So that's information about the rate of change of volume. Okay, now the water tank has a height of 10 feet and a radius of 5 feet, and those two measurements aren't changing. The tank is not changing size, so I can label those with those constant values. Now the question is, how fast is the water level rising when the water is 6 feet deep? So imagine what the water looks like as it gets pumped into this tank. Okay, so there's the top surface of the water. This water has some height and some radius. Okay, so our question is, what is dH over dt? How fast is the water level rising? I expect this derivative to be a positive value because as the water is pumped in, h should be getting larger. And we want to know dH over dt when the water's depth is exactly 6 feet. So, starting with the volume formula for a cone, 1/3 pi times the radius squared times h. Now, this is the first problem where we've run into this issue. There are 3 variables in that equation. We only have information about 2 of them. We don't know anything about the rate of change of the radius. We don't know anything about exactly what the radius would be at any particular time. So what we've got to do before we can go any further is work on this equation a little bit so that it just has variables v for volume and h for height. Now the key to being able to do this is to picture the right triangles here. If instead of drawing this height out here to the side, if I'd indicated that height there, then it is really easy to see a right triangle right there with one leg that's 10 feet and the other leg that's 5 feet. And then inside that right triangle, there's another one with one leg that's h and another leg that's r. And the way those right triangles are put together there, they're similar triangles. We know the sides of similar triangles are in proportion, so whatever the relationship r to h is for the small triangle has to be the same relationship of the radius and the height in the large triangle. So this is our key to being able to come up with some expression that we can put in place of r in our volume formula. So solving this equation for r, you're going to find that r is 1/2 the height. So if you take that and plug it back in our volume formula, then we're looking at 1/3 pi times the quantity 1/2 h squared times h. Cleaning that up, I'll have pi over 12 h cubed. Now differentiate with respect to t. Plug in the values that you know. simplify. Let's see, 36 divided by 4 is 9. So we have 9 pi there. So solving then for dh over dt, you're going to end up with 1 over pi. And this is another one of those times where it probably makes sense to actually get a decimal approximation for that, but it's okay for you to answer the question with the expression 1 over pi. Units on this, let's see, distance is measured in feet, so this would be feet, and time is measured in minutes in this problem, so feet per minute. So we would say the water level is, well, exactly how was that worded? The water level is rising. We have a positive derivative. At 1 over pi feet per minute when the depth is 6 feet.